Um, yeah, that right. That right indeed. What we're going to look at here, this is a problem that we either looked at in class or you had for homework. But what we're looking at here is how an angular velocity at all points on a rotating disk is the same because it takes the same amount of time at any point in the disk to go around the 2 pi, but how the linear velocity at any point is different. And if we have, here's my crudely drawn circle. If we think about this disk rotating like this, then if I'm on the inside of the disk running around in this small circle down here, I'm only covering a small distance or displacement in some amount of time. So my speed isn't very high. Whereas if I'm on the outside of the disk running and running and running and running, you've got to go much, much faster in order to achieve that. So whenever we have this here, we have these different velocities that are going on. We have a very large tangential velocity out here, and on the inside, we have a much smaller quantity. This is important for something like old record players because whenever they're putting the analog signal on the disc, whenever the needle's reading it, the data is going to be moving past that needle at different speeds. And you don't want your music to sound really quick like this whenever it's just moving and then get slow when it's at another spot. You just want the music to sound like it should, like it's played at the real speed. You don't want it to get all wonky as the needle moves around. So we need to figure out how fast the fly or the needle is at different areas on this disc. So erasing all of that. I want that to go away. There we go. So thinking about this, what we have is an old-fashioned LP or a record, and they rotate at 33 1/3 RPM or revolutions per minute, which you see that in your car all the time, these RPMs, but man, that is just a terrible unit in terms of doing mathematical quantities for it. It is a 12-inch diameter disc, though. These things are big if you've ever picked one up. Maybe your parents got one sitting around. Maybe you're really into audio, so you've got one sitting around. But these things are big. They have a diameter of 12 inches. Now, the inside of these things normally have a big label, and that label has a radius of 2.5 inches, okay? So what we want to see here is if there is a fly, the needle, if it's sitting on the edge of the disc out here, what is the tangential speed or the linear speed, v, at the outside point and then at the inside point as this thing is rotating consistently. So we're looking for two linear velocities or tangential speeds, one for the edge and one on the inside. The first thing we're going to have to do here is we are going to have to sort out this 33 1/3 revolutions per minute, because that's just a nasty little unit there. We're not doing anything crazy here. This is just a unit conversion to get it into something nice like radians per second. So if we've got 33.3 rev per minute, get a big train track going here. I know that there are 2 pi radian per rev, so the revs go away. And then there's, in 1 minute, there's 60 seconds, so the minutes go away there. This means that the angular velocity here, 33.3 times 2 divided by 60 is, I'm going to leave this in terms of pi because I like it like that. Our angular velocity here is equal to 1.11 pi. And if you wanted to multiply it by pi, you'd get 3.48. But these are radian per second. So that first piece there is just getting our omega, the 33 1/3 RPM, into a better unit. Now, if we want the tangential speed at the edge of the disk, we're looking for some velocity v, this isn't that crazy of a thing. We actually know what the radius is from the center of the disk going out. If the whole diameter is 12 inches, then halfway is just 6 inches there. So we know this radius here is 6 inches. We're just going to leave it in inches. We don't have to do any conversions to that. So if we want a linear velocity, we just have to do omega times r. So with this, we take 1.11 pi, and we're actually going to multiply by that pi. This is a linear quantity. We want it in just a number form, times 6 inches. And what we're going to get here, after we multiply all that out, 1.11 times pi times 6 inches, we're going to get a quantity of about 20.9, and our units here are going to be inches per second. Okay, kind of a weird unit, but it's what we have. If we do the exact same thing for the inside distance, we have the exact same angular velocity. Our angular velocity here is still going to be the 1.11 pi. Okay? What we're going to do, though, is we're going to look at a much smaller radius here. We're going to look at the radius of the label, that 2.5 inches. So what we'll do here is we'll just say, once again, that the linear velocity is the 1.11 pi radians per second times 2.5 inches. We multiply all that through. We get something much smaller, 8.7 inches per second. We know this value needs to be smaller here because it's on the inside of the disk. It's rotating slower. You're on the inside of that merry-go-round. But that's basically all we're doing. We're just doing one unit conversion in the beginning, recognizing that the disk is rotating as a whole so that our angular velocity is staying constant, and then just doing a conversion, which is on the back of our best friend. A tangential speed or a linear velocity is just omega times r, and then our problem's done. So with that, we here are finished.